Mic on.
There we go. Okay, start recording. Okay, so the first couple of these questions, I'm going to start off with the, I'm not sure which review this is. This is the one that's dated April 9th, 2010. Um, so these are the ones that we started off with this morning. I'm just going to do the full thing, and then in a separate video, I'll do the other review. Okay, so it says determine which of the following vector fields is the gradient of a function f of x. If it is, find all such functions. Okay, so the first one it gives us is v of xy equals 2x e to the y minus sine of x I plus x squared e to the y plus cosine of 2y j. Okay, so we're going to assume that this is the gradient of a function. So we're going to assume that v equals gradient of some function. Okay, I don't really care what function it is for now. But that means that um, the derivative of this function with respect to x is 2x e to the y minus sine of x. And also over here that the derivative of f with respect to y is x squared e to the y plus cosine of 2y. Okay, so that's because we assumed this was a gradient. Now, we know that the mixed second derivatives, so that's going to be the two derivatives df, so squared, dy dx, so the y derivative of the x derivative, should be the same as dx dy. Right, this was one of the properties of the partial derivatives, is that I can interchange them just fine. Okay, so here if I do the y derivative of the partial with respect to x, then I get, let's see, so this first term doesn't change. This is 2x e to the y. And then over here, the derivative with respect to x, I get 2x e to the y. Okay, so what this means is that, yes, I can write this as the derivative since these are the same. Okay, since these are the same, it means, yes, I can write v as the gradient of some function. So, yes, can find f so that v equals the gradient of f. We also say that f is v is a potential. Okay, if it's a potential vector field, then we can write it as the gradient of some function. Okay, typically we call this the vector potential, but in physics, something that has this property would be called conservative. That doesn't really matter for the review. Okay, so let's figure out what is this function. So I know that df dx is this thing, 2x e to the y minus sine of x. So if I integrate this with respect to x, what do I get? So the integral of this with respect to x is the integral of this. Let me move that over. Uh, 2x e to the y minus sine of x dx. Okay, so again, here x is my variable. I don't care about y. As far as I'm concerned, y is a constant. So this becomes x squared, or 2x squared e to the y over 2 minus, so integral of sine is negative cosine, so it's going to be cosine of x. So plus a constant, right? So when I integrate, I still need to add the constant. But remember, as far as I'm concerned, y is also a constant. So this is going to be some function of y, right? I don't know what this is, just some function of y plus a constant. And those twos cancel out. Okay, so now if I do the same thing for the y derivative, right? So I integrate the partial with respect to y with respect to y, I get, so this is going to be the integral of x squared e to the y um, plus cosine of 2y dy. Okay, so then I integrate this with respect to y, so I get, that stays as x squared e to the y, right? Integral of e to the y is e to the y, plus integral of cosine is sine. This is going to be sine of 2y over 2 plus some constant. And again, the same thing, as far as I'm concerned, x is a constant. So this is going to be plus some function of x plus a constant at the end. Okay, so notice real quick, this term appears in both things. So that's definitely going to be an f. Right, so both of these are supposed to be what my f is. Okay, but some of these terms just don't show up in the other one. So like this is a function of y, that's going to be lumped in here. This is a function of x, so that's going to be lumped in over here. So here I have f of xy equals, so x squared e to the y, right? And then terms that involve only x, that's going to be my cosine of x, plus terms that involve only y, right, these ones, that's going to be 1/2 sine of 2y plus some constant. I'm not going to box it. And that's my answer. Okay, part 2. So part 2, we have, we're going to do the same thing. We have that the gradient, we assume that w is the gradient of some function. I'm going to call it g this time, just so I don't get mixed up with the above. So that means that dg dx is equal to x squared minus e to the 2y, and that means that, let's see, dg dy is equal to 2xy e to the, let's see, that's minus e to the 2x. Okay, so if I do the second derivatives, I have d squared dy dx of g. So that's the derivative of the x derivative with respect to the y derivative. So that's just going to be minus 2e to the 2y. And then this one, d squared g dx dy, that's going to be 2y minus 2e to the 2x. So since d squared g dy dx is not the same as d squared g dx dy, so these are supposed to be true. So since I've found that these aren't true, no such g exists. Okay, so when I wrote this over here, I was saying assume this is possible, but we got to a contradiction, meaning that it's not possible. No such g exists. Okay, next page. Okay, number 2. If gradient, so this is number 2, of f of at the point 3, 2 is equal to 3i minus 4j. It says r of t equals 3 times 4t plus 1 I plus 2e to the 4tj, and h of t is the composition of f and r of t. Okay, so there's 2 ways to do this. The first way, oh, and it says find h prime of 0. So the first way to do this is just use, either way, it's going to be using the chain rule. That's all this is asking for. But there's 2 ways to write it. So the first way is h prime of t. So we want something like the derivative, and then we have to multiply by the derivative of what's on the inside. So this is going to be the derivative of f times r prime of t. So notice real quick, r prime of t, r is a vector, so r prime of t is also going to be a vector, meaning that this product right here needs to be the dot product, and this, whatever I have here, needs to be a vector, meaning that this is the gradient, not just like the derivative, it's the gradient of f at r of t. Okay, so I need to figure out r prime of 0 because we're trying to figure out h prime of 0. Well, r prime of t, this is just 12i plus 8e to the 4tj. And so r prime of 0 is just 12i plus 8j. R of 0, because that's what I need to plug in here, R of 0, that's going to be 3i plus 2j, right? Because e to the 0 is 1. So when we evaluate gradient at r of 0, that's the same as evaluating, let's see, so gradient of f at r of 0, that's the same as evaluating gradient of f at the point 3, 2, which, hey, look at that, we know what it is. That's 3 minus 4. Okay, so now h prime of 0 is equal to the dot product of these two. So that's going to be 3 minus 4 dot 12, 8, which is 36 minus 32, which is 4. Okay, let me just mention the other way you could do this. So instead of writing it as gradient of f dot r prime, I can also write this as h prime of t is going to be the sum of all of the derivatives. Don't worry about that. So this is going to be d, df let's see, so this is a function of x and y. X dx dt plus df dy dot dy dt. Okay, so here r of t, that's going to be our x of t and y of t. All right, so I could do the partial with respect to x, multiply by the derivative, the full derivative. These aren't partials because they only have one variable. And I could actually multiply those by the derivative of x and the derivative of y. And I'm doing the same computations, it's just writing it down in a slightly different format. Okay, so number 3. It gives us that f of xy equals x cosine of y plus y cosine of z plus z sine x. And it tells us to find fxx plus fyy plus fzz. So if you're not familiar with this notation, this just means the second derivative of f with respect to x squared plus second derivative with respect to y plus second derivative with respect to z. Note real quick, this is not the gradient of the gradient. It's kind of similar, but it's not the gradient of the gradient because that would give us it not a scalar. This is going to be a scalar when we're done. So I'll just find each of these individually. So df dx, this is cosine of y. Next term is 0 plus z cosine x, and then df, let's say fxx, fxx. So that goes away, and then we're left with minus z sine of x. Okay, df, or I'll just put fy, the derivative of f with respect to y is, so that's going to be minus x sine y plus, let's see, the y goes away. This is just cosine of z, and then the last term goes away. So fyy is going to be derivative of sine is cosine. That's minus x cosine of y, and that goes away. So finally, fz, first term vanishes. So derivative of cosine is negative y sine z plus, it's just going to be sine of x. So fzz, that's a z right here, is, let's see, so the second term vanishes, and I just have minus y cosine of z. So to for the final answer, um, we have, so fxx plus fyy plus fzz. That's minus z sine of x minus x cosine of y minus y cosine of z. And that's my answer. Okay, next page. Okay, find an equation for the tangent plane and scalar parametric equations for the normal line tangent, for the normal line to the surface. So it gives us the surface. This is number 4. xy squared plus 2z squared equals 20. And it tells us find the tangent plane and the normal line at the point 2, 1, 3. Okay, so the first thing I need to do to find the tangent plane is I need to find a vector that's orthogonal to this surface. Okay, so this describes a surface. So what I do, and I don't actually need to do in this one, I need to move all of my variables to one side, on the left side, and all of my constants to the other side. Okay, so that way this describes a level set, right? So this function, this is the level set, all of the points where this function equals 20. I'm going to call this g of x, y, z. That's going to be x, y squared plus 2z squared. Okay, so this is some function, and the surface that I'm interested in is all of the points of this function on this whatever curve this is, where this equals 20. So that describes a level set, and I know that gradients, so the gradient of g is going to be orthogonal to the level set. So, or the level curve or surface, whatever. Okay, so I want to find the gradient, and that's going to be my vector that's orthogonal to the surface. Okay, so the gradient of g is what? Let's do a row. Derivative with respect to x, that's going to be y squared. Derivative with respect to y, that's going to be 2xy. And with respect to z, that's going to be 4z. Okay, so gradient of g at the point 2, 1, 3 is, it's going to be 1 squared, that's 1, 4, and 12. Okay, so that's going to be my direction vector, or my normal vector. So this vector is normal to the surface. So for the tangent plane, right, this is going to be, I have my point on the plane, right, that's my point, and I have my direction vector, that's this. So I have x, y, z dot 1, 4, 12 equals my point dot 1, 4, 12. Okay, so I do the dot product. I have x plus 4y plus 12z equals, so it's going to be 2 plus 4 plus 6 equals 12. So that's my equation for the tangent plane. Let me just note real quick, another way I could have done this a little bit faster is I could have just written right away, this is going to be 1 times x minus 2 plus 4 times y minus 1 plus 3 times z minus 12 equals 0. And this is also going to describe, it's going to be the same thing, right? It's just moving this, this over to the other side with subtraction. That's a, I messed that up. That's supposed to be a 12, so this is not correct. So that's 2 plus 4 plus 3 times, that's 36, 42. And you get the same thing. It's just two different ways to write the same thing. This is a y. Okay, so that's the tangent plane. Now I need to find the line normal to the surface at that point. Well, so now I need a point on the surface and a direction vector, right? So here we had a normal vector, but the direction vector is going to be the same thing, right? The direction is in the direction of the gradient. So this is my direction vector, this is my point. So my line, what do I call it? I don't know, L of t, right? That's just going to be um, the direction 1, 4, 12 times t plus 2, 1, 3. So that's going to, and it says it wants the scalar parametric equations. Right, so this tells me that, actually, you know what, let me just write it this way. X of t, y of t, z of t. So this is part B. So this tells me that x of t is going to be t plus 2, y of t is going to be 4t plus 1, and z of t is going to be 12t plus 3. And that's my answer for the normal line. Okay. Question 5. Find a unit vector in the direction in which the function, so let me copy this function, f of x, y, z equals x squared z e to the y plus x z squared. Okay, so find a unit vector in the direction in which the function increases most rapidly. So at the point 1, ln of 2, 2. So if we're on this surface, right, this describes some sort of surface, and we're at the point here, and we look around, and we want to know what direction is the surface the steepest, right? What is the direction of steepest increase? Okay, so the fact that you should know is that the direction of steepest increase is the direction of the gradient at that point. Okay, so I need to find the gradient and then evaluate it. And that's going to be the direction of steepest increase. So then I need to find a unit vector for that direction. So I'll just normalize it after that. Okay, so gradient of f is going to be, so the derivative with respect to x, that's going to be 2xz e to the y plus z squared. Then we have, that all stays the same, squared z e to the y. Second term vanishes. And then we have x squared e to the y plus 2xz. So then I evaluate this at 1 ln of 2, 2, and I get, so xz, that's going to be 4, e to the ln of 2, that's going to be 2, plus 4, and then I have 1 squared times 2, so 1 squared times 2, that's 2, times 2, that's going to be 4, right? E to the ln of 2 is 2. And then I have 1 squared times 2 plus 2 times 1 times 2, which is 2. So that's going to be 12, 4, 8. So that's the direction of steepest increase, okay? So if I'm at this point, the direction in which it's steepest is in this direction, so we normalize it. So the norm of this vector, 12, 4, 8, uh, 144 plus 16 plus 64. Let's see, so I can factor out a 16 from each of these. All right, so that's 4 times 4 times 3 times 8. So it's going to be 4 square root of, what is that? That's going to be 9, right? 9 times 16. Yeah, that's right. Okay. Plus 1 plus 16 times 4. So that's 4 root 14. That can't be simplified. So my answer is 12 over 4 root 14. That's going to cancel with a 3. And then I have the 4's cancel, so I get 1 over root 14. And then again, the 4 and the 8 cancel, so I get 2 over root 14. And actually, no, okay, that's fine. So this is going to be 3 over root 14, 1 over root 14, and 2 over root 14. And that's my answer. Okay, page append. What is the directional derivative of f at that point? Okay, so I still need that same information. So we want to know what is the directional derivative in this direction at that point. Okay, so how do we find the directional derivative? We do the direction, which needs to be a unit vector. Sorry, let me do it the other way. The gradient of f dot the direction vector, which needs to be a unit vector. Okay, so I'm going to do some simplification first so we can see something real quick. So here, this is the gradient of f, and then how did I compute this this direction? That was just gradient of f divided by the norm of gradient of f. So here we have gradient of f dot gradient of f, which is gradient of f squared, gradient of f squared. Squared over gradient of f. Gradient of f. So those cancel, and we have that the directional derivative in the rate of steepest increase. Okay, so this direction is depends on what direction we want. In this case, we wanted the rate of steepest increase. When that happens, this is just going to be equal to the norm of the gradient of f at that point.
Mic off. Mic on.
Okay, so that makes it rather simple to calculate because we already did. The gradient of f at that point was 12, 4, 8, and we already computed the norm. So this is going to be 4 root 14. Okay, so if it wasn't the direction of steepest increase and I just wanted the directional derivative, then I would have just computed the dot product and be done with it. It's not hard to compute. So like this next one. So part C says find the directional derivative of f, I'll need to look what f is again, in the direction of, I'll say d equals 2, 6, 3 at the point 1 ln of 2, 2. So it's the same question, find the directional derivative of that function. So it's going to be the same thing as above, gradient of f dot d hat, right? I need to normalize it. So I know what the gradient is at that point. That's going to be 12, 4, 8. Okay, and then I need to normalize d. So the norm of d is, what is that, 4 plus 36 plus 9 that's 49, 7. So that means that d hat, my unit vector, is going to be 2 over 7, 6 over 7, 3 over 7. Now to find the directional derivative of f, right, so on the surface f at the point 1 ln of 2, 2, the slope in the direction of d is, so that's going to be 12, 4, 8. So grad f dot d hat equals dot 2 over 7, 6 over 7, 3 over 7. That's going to be what? That's 24 plus 24 plus 24 all over 7. Is that right? Yeah. Which is 3 times 24. 3 times 24. I don't know what that is. 3 times 24 over 7. That's going to be 72 over 7. So that's the slope um, of this function in the direction of d at that point, right? If we were to change the point, the slopes are going to change completely. I have no guarantee on how that changes. Okay. Number 6. Find the maximum and minimum values of the function f of x, y is x squared minus 6x plus 2y squared minus 16y plus 21. On the domain D, which is the set of all points such that 2 is less than or equal to x less than or equal to 5, and 1 less than or equal to y less than or equal to 6. Okay, so if you remember real quick from Cal 1, if I have some curve and I want the maximum and minimum values, then I can do the derivatives, take where that's equal to 0, but I also have to, if I'm not looking at the whole real line, I have to remember to include the endpoints. Okay, because these could also be the maximum or minimum values, which in this case they are. So the equivalent of this is we have to check the boundary of this set. Okay, so we'll do the gradient, set it equal to 0, but then we need to go back at the end and check the boundary to see what are the maximum and minimum values on the boundary. So this kind of a question is a bit of a pain, but it's not conceptually difficult. Okay, so first let's just find the local max and min. So the gradient of f is equal to what? So this is going to be 2x minus 6. Then we have 4y minus 16. And we set that equal to 0. So this tells us that um, 2x equals 6. So x equals 3. And it tells us that 4y equals 16 and y equals 4. So the point 3, 4 is a local max or a local min. Now, which one is it? Okay, so this is what I need to do the second derivative test for to figure out if it's a local max or a local min. Okay, so here I'm going to make the matrix of second derivatives. So df dx squared, d, df dx dy, df dy dx. So remember, these two here are going to be the same, and then d squared f and dy squared. So let's fill this in. So the second derivative of the x, or the second x derivative, that's going to be a 2. I do the derivative of the x component, or the x derivative with respect to y. Sorry, I do the derivative of the y derivative with respect to x. That's going to be 0. So that's also going to be 0. They're the same. And then I do the derivative of the y derivative with respect to y again. So that's going to be 4. Okay, so now I look at the determinant of this matrix. So that's going to be this minus this. So I'm looking at, so I'm going to call this H. Technically, this is called the Hessian matrix. So I'm looking at the determinant of H, which is 2 times 4 minus 0 times 0, which is just 8. Okay, so if this is negative, we have a saddle point. If this is positive, then we look at the values along the diagonal. Okay. If it's 0, then it's hard to determine. It's not really a local max or a local min strictly. Okay. Um, so the way we say is test is inconclusive. It's not really like actually inconclusive. We just don't really care about it, about that condition in this class. Okay, so if it's positive, what I'm going to look at is I'm going to look at the sum of these two. Actually, I don't even need to look at the sum. I just need to look at one of them because they're going to be the same sign. But basically, they're both positive. Okay, so they're both positive, meaning that the shape is going to look like this. It's kind of like when the second derivative is positive. It's concave up, meaning that the point that I have is a local minimum. Okay, if this was negative, right, if one of them was negative or if they were add up to something negative, then this would be a local maximum. Okay, so I'm going to remember that. This is a minimum. Okay, that's not my answer yet. I still need to check the boundary. Okay. So real quick before I go to the next page, what does the boundary look like? It looks like this. So really, this is just a set of 4 lines, right? So this is x equals, but I'm going to write each of these lines in parametric form. and then find the minimum along each of those lines. Okay, it is also possible to do this with a Lagrange multiplier, although this example would be a bit of a pain. But you could say, find the minimum of this function given that we have to stay along the boundary, right? And we could find other minimums as well. Okay, but I'm going to do it this way with a parametric form. Okay, so here, let's do this line right here. I need a different color. Let's do this line right here. So what is the equation of this line? This is going to be the line. Let's see, we have x is fixed constant at what point? So x is going to be 2. Let me change that to blue. And then y goes from 1 to 6. Okay, so we can say that this is going to be 1 plus t, where t is in the range from 0 to 5. Right, so this is just a parameterization of this line. It really doesn't matter which parameterization, just as long as I have it in terms of one variable. So now I can rewrite f. Let's leave f on the screen. I can rewrite f in terms of this. Okay, so I have f of 2 and 1 plus t, right? That's x and that's y, because we're sticking only along this line. This is going to be 2 squared minus 12 plus 2 times 1 plus t squared minus 16 1 plus t plus 21. Okay, so let's find the maximum and minimum along that edge. How do I do that? I'm going to take the derivative with respect to f. Actually, no, I didn't even, did I need to do that? Take the gradient. Yeah, I actually didn't need to plug that in. I'll do it that way in the next one. Okay, so I do that, and I plug that in. So that's a constant. That's a constant that goes away. Here, this is going to be 4 times 1 plus t. And then, let's see, the 16 is going to go away. I have minus 16t, and then the constant goes away. So I have minus 12t plus 4. And I set that equal to 0. So that tells me that t is equal to, let's see, move that over, 1/3. So at 1/3, what are my corresponding x and y values? That's going to be the point 2 and 4/3. Also, don't forget though, I need to include the edges, or the corners. Okay, so the possible max or minimum along the edge is going to be here, or along this edge, it's going to be here, the point 2, 1, and the point 2, 6. So those are my possibilities here. I'll come back to those. Now I need to do that same thing for the other points. Okay, so let's do next a different line. Let's do this one. So this is going to look very similar, except now we have y is fixed at 1, and x goes from 2 to 5. So x equals 2 plus t from, let's see, from 0 to 3. Okay, real quick, one thing that I forgot to mention is that here, when I got this point on the edge, this 2 4/3, I need to make sure that that's actually on the line. In this case, it is, right? 4/3 is definitely in between 1 and 5. That's fine, but I do need to make sure that it's actually on that portion of the line. Okay, so I want df dt. I can also use the chain rule for this, okay? So this is going to be gradient of f at, now we're sticking to r. So here, this is going to be my r. So this is r of t is going to be 2 plus t, 1. Dot r prime of t, right? So this is going to be gradient of f, which we saw up here, is 2x minus 6. So 2x, x is what? X is 2 plus t minus 6. Oops, that's not. Yeah, I do want that. Okay, 2 minus 6. And then I have 4y minus 16. So that's 4 times y, which is 1, minus 16. Dot r prime, which is going to be 1, 0. Right? Yeah. Okay, so that becomes 4 plus 2t minus 6, which is 2t minus 2. So again, this was the derivative of f along this line with respect to t. We want to find the maximum or minimum, so we set this equal to 0, which tells me that t equals 1, which corresponds to the point 3, 1. Also, I still need to include the edge points, right, the corners. So that's going to be, we already included 2, 1 up here, but that's also going to be this other one, which is the point 5, 1. Okay, let's remember that. Okay, next edge. It's really just going to be the same thing for each of these edges. So let's do this edge here. So here we have the line, so x is going to be fixed at 5, and y, again, is 1 plus t for t in, oh, let's just write it this way. 0 less than or equal to t less than or equal to 5. Okay, this way ended up being a lot faster. I'm going to do it that way again. So I have 5 and 1 plus t. So df and dt is going to be gradient f r of t dot r prime of t. So gradient of f, that's, let me copy that actually. Um, Come on. Okay. Okay. So here, Gradient of f at r of t, so r was 5, 1 plus t. So this is going to be 2 times 5 minus 6, 4 times 1 plus t minus 16, dot the gradient, or the r prime, so that's going to be 0, 1. So that's going to be, first thing is 0, and then we have 4 plus 4t minus 16. So that's 4t minus 12. Again, we do the same thing, we set that equal to 0. So we have t equals 1/3. So that's very much the same as the first one, except now this is actually the point 5 1/3. Oh, sorry, not 1/3. 5 and 4/3. Okay, last edge. This one. Oh, and I need to remember to include the corner. Okay, so I need to remember to include the corner here. This is going to be, so y is fixed equal to 6, and x is going to be the same as over here, 2 plus t, with t in the range 0 to 3. And again, I've been kind of bad about checking that t is actually in my range, but t is equal to 1, t is equal to 1/3. Yeah, those are in my range. So df dt, same thing as before. Dot r prime of t. Okay, so we have 2 plus t and 6. So 2 times 2 plus t, and then 4 times 6 minus 16, dot r prime, that's going to be 1, 0. Which is 2t minus 6, no, that's 4 plus 2t minus 6 plus 0. That's going to be 2t minus 2. Set that equal to 0. T equals 1. Okay, and this tells us that at t equals 1, we have this is 0.36. So t equals 1, that's the point, yeah, 36. Okay, and the fact that these were the same in both cases is a complete fluke. They don't have to be symmetric at all. They don't have to exist either, right? If you get something where the derivative is never 0, that's definitely possible, right? If you have a line that's always increasing, the derivative is never 0. You just need to make sure to include the corners. Okay. Oh, and then I need to include the corner, which is the point. What 6? No. 5, 6. Okay. So my final task, and let me copy this one down here, is 3, 4. My final task is to plug all these points in. I know that's a local min. So I need to plug all these points in and figure out which one is the actual maximum and which one is the actual minimum. Okay, and notice real quick, most of this problem that I've had, right, this whole page here, all this work, has been because I included the boundary, right? Because I had like this edge where it equals 2 and x equals 5 and y equals 1 and y equals 6, right? If I didn't have that and we were looking strictly at the interior of this set, I wouldn't have to worry about this. I'd only need to look at local max and local min. There wouldn't be a boundary, right? If I had 2 less than x less than 5, 1 less than y less than 6, if I had this, I wouldn't care about the edges. But this is a closed set, so I have to take those into consideration. Okay, and let's copy my function down. That's not going to be fun. Not going to be fun plugging all these in. Okay, and paste. Let's try that again. Copy. Paste. Okay, so let's do these ones. So we plug in 2 and 4/3. So we will have, I don't need that anymore. F of 2 and 4/3. That's going to be 4 minus 12 plus 2 times 16 over 9 minus 16 times 16 over 9 plus 21. That's minus 8 plus 21. That's 13 plus 32 minus 1. 16 squared is what? Oh, 256. For 9. 13 times 9, that's 97? No, 107. Minus 256 minus 32, that's going to be minus 224. Yeah. And we do that subtraction and we get negative 117 over 9. And that's not divisible. Okay, so that's value, so that's probably going to be a minimum or something. If I plug in 2, 1, I get, so that's 4 minus 12 plus 2 minus 32 plus 21. Nope, y was supposed to be a 1, so that's 16. So that's 6 minus 6, and that's minus 22. So that's going to be minus 1. And then f of 2, 6, that's going to be 4 minus 12 plus 36 times 2 is 72, minus 16 times 6 plus 21. That's 64 plus 21. 16 times 6, that's 32 times 3, that's 96. Okay, so Alexa, 85 minus 96, that's minus 11. Okay, so along that edge, we see that the minimum is going to be I think it's this one, right? Because that goes into that. Let's see, how many times does that go in? That goes into that one point. Yeah, so this one's actually the smallest. This is the minimum along this edge. And this is the maximum. So far, okay, so we still need to keep checking. So f of 3, 1, that's going to be 9 minus 18 plus 2 minus 16 plus 21. That's minus 9 minus 7. Right, hold on. So that's minus 9 plus 2 minus 7 minus 23 plus 21. That's going to be minus 2. And then here, 5, 1, that's going to be 25 minus 30. Plug in 1, so we get plus 2 minus 16 plus 21. Let's get this over. Okay, so that's minus 5 plus 2, that's minus 3, that's minus 19, minus plus 21, positive 2. So, okay, we can update this now. This is still going to be the minimum. This is a little bit bigger than negative 11. It's almost negative 12. And here, though, this is no longer the maximum. This is the new max. Okay. Now we plug in f of 5 and 4/3. So this is 25 minus 30 plus 2 times 16 over 9 minus 16. Oh shoot, I did this one wrong. I did this wrong because that's not supposed to be 16 over 9. That's supposed to be 4/3. I will come back to that as soon as I finish this one. This is 16 times 4/3 minus or plus 21. Dang it. Okay, so that's going to be minus 5 plus 21. That's 16. Plus 32. 16 times 4, that's 64. It's minus 64 over 3. Let's do try that random selection. Okay. Let's see, so 64 times 3 is what? It's 12, 1, 18, 19, 192. And 16 times 9 That's going to be 4, carry the 5, 9, 144. Oh, I knew that. Okay, so that's 144 plus 32 minus 192 all over 9, which is 176 minus 192 over 9. What do we need? 4, it's 6, 16 minus, is that right? 76 plus 16, yeah, that's right. Okay, so minus 16 over 9. Okay, so actually, so far, that's not the minimum. No. So 16 over 9, that's what we get here. Okay, now I need to go back and redo this one because my numbers were wrong. This was supposed to be 4 over 3, meaning that this is all wrong. All right, so we still have, so that's minus 8. Okay, so 13 is still right. And I have 32 over 9 minus, the same math still works though, so I can copy that. This was 192 over 9. Okay, and 13 times 9 is what? That's, okay, the 107. So that's 107 plus 32 minus 192 all over 9. 139 minus 192 all over 9. What is that? That's a 3. And that gets us to 4053 over 9. And that's almost minus 6. So yeah, so far this is the minimum still, surprisingly. Okay, almost done. Oh my gosh. We checked that one. Okay, so we just have these ones to check here. 3, 6, 5, 6, and 3, 4. Okay, so f of 3, 6. Let me circle that so I can find it later. Circle that, that. Oh, actually, no, that's the minimum now. Minus 11. Okay. I really don't think you guys would have a problem like this on the exam. If you did, it would just be finding the local max and local min. Okay, f of 3, 6. So we have 9 minus 18 plus 2 times 6 squared, which is 36. 2 times 36 is 72. What did I write there? That's 18. Plus 72 minus 16 times 6 plus 21. So 72 minus 9, that's going to be 63 plus 21. 16 times 6 is 96. So that's 84 minus 96. That's a 6 and a 6, so that's 12 minus 12. Okay, so that's the minimum so far. Okay, 2 more. Okay, two more. F of 5, 6. So that's going to be 25 minus 30. This part's the same, so it's plus 72 minus 16 times 6 plus 21. So that's minus 5 plus 21. So minus 5 plus 21 is going to be 16 plus 72 minus 96. So this is 88 minus 96, which is negative what? 2 and 6, negative 8. Okay. So it still doesn't beat the negative 12. Okay, and last one is the local max, or sorry, the local min that we found. Okay, so this is at 3, 4. Of 3, 4 is, so that's going to be 9 minus 18 plus 2 times 16 is 32. Okay, so 2 times 16 is 32 minus 64 plus 21. Hey, nice numbers finally. So that's minus 9, 16, let's see, 32, that's minus 32 plus 21. So that's going to be a lot. Actually, hold on. Minus 9, and that's minus 11 equals minus 20. Okay, so our maximum, the maximum number that we got was this one right here, was 2 at the point 5, 1. And the minimum that we got was this local min, which was minus 20, that was the minimum value, at the point 3, 4. Right, so this was min, and this was max. Okay, so notice real quick, on this boundary, right, there has to be a maximum value somewhere, okay? But when I did the critical points, I only got 3, 4, right? That's, I don't know, somewhere right there, right? So I only got 1 point, but there's still a maximum somewhere. How do I find it? Well, it's going to be on the boundary somewhere, and I need to check along the boundary, okay? So to recap, I wrote each of these as a line, and then I did the derivative of f restricting to that line. You can do that in two ways. You can either substitute the parametric form and then do the derivative with respect to t, or you can use the chain rule, which is what I did for most of these because it turned out to be nice and simple. And then, so those give you all of your points, all of your critical points on this domain. And then you plug them in and you check which one is the actual max or min. So in this case, we're not looking for local max or local min, we're looking for absolute max and absolute min. I doubt you would have one that long, and I hope I don't have to grade one that long. Next question is nice and short. 7. It says f of xy is y cubed over 3 plus 2xy plus x squared minus 3y. So it says find all of the critical points of the function and determine whether each critical point yields a local max or a local min or a saddle point. Okay, so here we don't have a domain, so we don't need to worry about the boundary thing that we did in the last one. Here we just need to do the gradient and look at the gradient and the Hessian matrix, right? So that's the matrix with the second derivatives. So the gradient is, that's going to be 2y plus 2x, and then this is going to be y squared plus 2x minus 3. So the critical points are when this is equal to 0. So I set this equal to 0. When it's 0 or, yeah, when it's 0. Okay, so here I have y plus x equals 0, right? I divided both sides by 2. So I have y equals minus x. And then I also have y squared plus 2x equals 3. Plug the negative x in, and I get x squared plus 2x equals 3. Move that over, so I have minus 3 equals 0. And we factor x minus 3 plus 1. No, plus 3 minus 1. That's my eraser. Minus 1, so x is equal to 1 or minus 3. So here we have, so if x is 1, we have the point, we have the point 1 minus 1, right? I just take x and I plug it in over here. And the point minus 3, 3. So those are my critical points. Now I need to determine if they are max or min, right? So these are the points x, y. So I'm going to create the Hessian matrix. Right, so this is the matrix of all of the second derivatives. Right, so this is d squared f dx squared, d squared f d x dy, d squared f dy dx d squared f dy squared. Okay, I already have the first derivatives done. Those are in the gradient. So the derivative, the x derivative of the x derivative, that's going to be just 2. The y derivative of the x derivative, that's also going to be 2. They have to be the same, so here we go. And then the y derivative of the y derivative, that's going to be 2y. Okay, so real quick, notice the second derivatives depend actually on x and y, right? This is actually kind of a function almost. So let's plug in our points. We have 1 minus 1. That's going to be 2, 2, 2, minus 2. Okay, so the determinant of this, that's going to be minus 4 minus 4, which is minus 8. So since this is less than 0, this tells us that 1 minus 1 is a saddle point. Okay, now I do the same thing for minus 3, 3. And I have 2, 2, 2, 3. So now I get 6 minus 4, which is 2. Okay, so this is positive. So this tells me that it's either a minimum or maximum, but not which. Okay, for that, I need to look at what is the sum of these two, right? So is that positive or negative? So that's not equal to 2. The determinant of that is equal to 2, which is bigger than 0. So I need to do an additional check. So now I'm going to look at this. Is this bigger or less than 0, right? That's just the sum of the values along here. And this is going to be positive. I don't care what, it's 5, but it's positive. Okay, so since this is positive, right, second derivatives are positive, that corresponds, like I said, to concave up, what we call a convex function. Okay, so here, whatever point we have, it's going to be a minimum. If the determinant would have been positive and this would have been negative, it would have been a local maximum. And if we get the point where it's 0, it doesn't really correspond to a local max or min. Okay, it kind of corresponds to a place where all of the points around it are low. Okay, and that's all for this review. I'll be uploading this, yeah, whatever.